Welcome to spectroscopy. We're going to talk about IR, mass spec, and NMR. Which of the bonds shown in red are expected to have IR active stretching frequencies? So you got to look at the bond. So in this bond, carbon-carbon triple bond, you have an sp carbon and sp carbon, and they're both connected to a hydrogen. So the dipole moment here is 0. And this would mean that this is inactive. So we're just going to write no. Okay, no IR. This bond here, we have an sp carbon and a hydrogen. So there would be some kind of polarity difference there. So this would be yes. That would be active. This one here, we have an sp and an sp carbon, but one is connected to a methyl and the other one a hydrogen. So this would be yes, it would be IR active. And it would probably be weak. This one here, the answer is no. That would be inactive because it's symmetrical and there's no dipole moment. This one here, we have an sp carbon with an sp3 carbon, and so that would be yes, that would be IR active. This one here, we have an sp3 with an sp3, and they're both connected to hydrogen, so this would be inactive. So the dipole moment is 0. Here we have a carbon and a hydrogen, so this one's yes. This one here is going to be weak, just because there is a dipole moment. And this one would be, this is different here, an sp3 and an sp2 carbon, so this one's yes. And this one would be yes as well, and it would be weak because, but you got a methyl and a hydrogen, so they're different. Okay, so spectra are given for the 3 compounds. Each group has more than one of the following functional groups. So we're going to look at these different functional groups and we're going to determine which of the spectra. So the first spectra we see is A, and the key peaks here are these NH peaks here. So these NH peaks. And as you can see, they're around 3,300 centimeters. And then we also have a peak here. And this peak is a carbon-carbon double bond. And that would be at around 1640 wave numbers, cm to the -1. So this would be a secondary amine. So this would be a secondary amine. This next one here, the first thing you want to look at, you want to see that you have a carbonyl. So you have a carbonyl peak, and that is around 1700 wave numbers. And you also have this peak here, which is a broad OH peak. And that broad OH peak makes this a carboxylic acid. This spectra here, there is no carbonyl peak. So we do not see a carbonyl peak in this. There's no carbonyl. We do see a OH alcohol here. So this peak here around 3,400 is an alcohol, and so that would be an alcohol. So IRs are good for telling you if you have what functional group you have or what functional group you do not have. Okay, the next one are more IR compounds, and we're looking for functional groups like conjugated ketone ester, amide, nitrile, alkyne. Okay, so when we look at this first spectra, we see that we have this small peak. First thing you always look at is here. So 1685 centimeters, reciprocal centimeters wave number. That is that's kind of low for a carbonyl. So the fact that it's low, but it's a strong peak, is probably conjugated. Okay, so it's a conjugated carbonyl, and there are no overtones around 27 and 2800. So because there's nothing else, this would be a conjugated ketone out of our selection. So go back to the selection and see what you can choose from. Okay, this one here, we have this peak here at 1738 centimeters. So that's showing you a carbonyl. It's pretty high ranging. And then what else do you have here? Since that's higher than a ketone's usually around 1710 centimeters, and they used to have the overtone at 27 and 28. I would say that this is going to be an ester. So that would be an ester. And then this next one here, we have this peak here, and this peak is kind of a moderate peak. It's around 1640 centimeters, reciprocal centimeters. We also have this peak here, and there's two humps there. It's not broad like an OH. So even though we have this carbonyl, we also have two peaks here, so this would be an amine. So the amine plus a carbonyl would be an amide. So it's probably a secondary amide, which means the nitrogen has two hydrogens on it. Okay, so for each spectra, interpret all the significant stretching frequencies above, this is not showing you that, but it's above 1580 centimeters, reciprocal centimeters. Okay, so the first one is this 1642, and this would be an alkene. And then the other ones we would have is this about 3080 centimeters, and that would be this carbon hydrogen here coming off of an alkene. So this would be an alkene. Okay, the next one we have this 1626, which is an alkene. We have 1691, which would be a conjugated carbonyl. So you're looking at something like this, an alkene right next to a carbonyl. And you see you have these two peaks here, around 2700, and you have another one around 2800, which tells you that this is an aldehyde, a conjugated aldehyde. Okay, so some of these compounds we can't see. We're supposed to figure out how we would distinguish between the following pairs. So first let's draw 2-methyl, 3-dimethylbutene, and so butene is there, and then we have 2, 3, that butene. So this is going to be basically IR inactive. There's really no dipole moment there. This compound here, you're going to see the carbon hydrogen, and that should show up around 3,080 centimeters. And then of course you'll see the carbon-carbon double bond, and that'll be around 1640 centimeters, reciprocal centimeters, wave numbers. Okay, so the next one is cyclohexa 1,3-diene and cyclohexa 1,4-diene. 1, 2, 3, 4. Okay, so when you look at this, this is conjugated. This is sp2, 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 sp2. You look at this one, it's isolated. So you have sp2, sp2. This is sp3, and then we have sp2. So you know you have the carbon-carbon alkene peak, and that is between 1620 and 1640 reciprocal centimeters. Let's just call it wave numbers. That's for conjugated. The isolated are more like 1640 to 1680 centimeters, or wave numbers. Okay, so what we're not seeing here is C under here, so you can refer to your paper, but you basically have this compound and this compound. So look at the functional group differences. This is a ketone, and this is an aldehyde. So you're going to see the carbonyl peak both around about 1725 wave numbers, but the aldehyde peak is going to have two peaks at the 2700 and the 2800. You're not going to see that in the ketone. Okay, so D, you have a carboxylic acid, and you have an alcohol. So this will be, so for this one, the carbonyl is going to be around 1710, and the carbonyl for the aldehyde is going to be around 1725. But you're also going to have the two peaks here at 2700 and 2800. You're not going to see that in this one. And then you're also going to see this broad OH. So it's going to be very broad, and it's going to be around 2500 to 3500. And this OH is going to be kind of, it's going to be broad and strong around 3300. Okay, so here we have an alkyne. And the alkyne, you have the carbon-carbon double bond, and that's around 2100 or 2200. But you also have the CH here, and that CH is going to be around 3300. For the nitrile, you're going to see something that's going to be more like 2200 to 2300, and you're not going to see this CH peak here. Okay, so we have an amide versus a ketone. The amide you're going to see, and it's going to be lower frequency than your ketone. So this carbonyl is going to be around 1650, whereas this carbonyl is going to be more like 1710. You're not going to see any more peaks for that ketone. But for the amide, you're also going to see likely two peaks around 3300, showing you that it's got two NH bonds. Okay, so we have an alcohol versus a ketone. So you're going to see this around 1710, that ketone. This one, you're not going to see that that carbonyl, but you'll see a broad peak around 3300 for that OH stretch. Okay, so for infrared, spectra is shown corresponding to four of the following compounds. For each of the spectra, determine the structure and explain how the peaks in this spectra correspond to the structure you chose. Okay, so we're going to match these structures with the spectrum. And so let's look. First of all, you look for a carbonyl, and you see if you have a carbonyl. There's no carbonyl, so there's nothing between around 1650 to, there's nothing around 1650 to 1800, okay? You do have this 1604, so around 1600, that peak is an aromatic ring. Okay, so when you see that these structures have aromatic rings. So they're that benzene or the phenyl ring. And you also see here that you have this broad peak around 3300. That's an alcohol. That's your OH stretch. So this is clearly the alcohol, the aromatic alcohol. Okay, looking at this peak here, you see that you have a carbonyl peak, and that carbonyl peak is around 1715. And then you also see that is it 17? Sure, maybe 1600, 1700, 1700. You also have this big OH peak, okay? This OH stretch. So that's telling you that you probably have some kind of carboxylic acid. And then you also have this peak here, and that is 1640, which is indicative of an alkene. So I would match this spectra with this alkene carboxylic acid structure from above. Okay, and the last one here we have the carbonyl peak. This one's probably around more 1715. And I don't really see anything else. Okay, so I don't see any alcohol around 3500. I don't see any amines around that. I don't see any peaks at the 27 and the 2800. It tells me it's an aldehyde. So out of all the structures, I'm going to go with the ketone. That's the ketone. And then we have this structure here, and this structure we have the most defining peak is this one here, and this is around maybe 2250. And we also have something around here that's around 1600, which is your aromatic ring. The 2250 is indicative of a triple bond, so we do have a nitrile to choose from. So the structure above that I would match the spectra with would be the aromatic nitrile. Okay, so the 3 IR spectra are shown corresponding to 3 of the following compounds. So once again, we're matching the structure and explaining the peaks in the spectra. So we'll need to refer to these. Okay, so the first one we have is we have a weak peak here around 2100. Okay, and then we have a strong peak here, and that strong peak's around 3300, which is so anything around the 2300 is a triple bond. And then in this area between 3000 and 3400, you have either, OH or NH or CH. And so this is actually a terminal alkyne. So the structure for that would match this compound here from above. Okay, the next structure we have we have this carbonyl peak, and that's the first thing you look for, 1720. And you also have these defining peaks here around 2700 and 2800. And that is indicative of an aldehyde. So we'll write down aldehyde, and then we'll look at our structures, and we'll look for the aldehyde. And we do have an aldehyde here. So that also tells me that we probably have a 1600 peak right here that says we have an aromatic group. That's important to see. Okay, point out which of these 4 mass spectra. All right, so we're done with the IR, and then we're going to look at the mass spectra, and then we might bring it all together. So these next questions have to do with mass spec. Okay, so when you're looking at mass spec, you want to quickly determine if you have a sulfur, chlorine, bromine, or nitrogen. And nitrogen, you're going to have an odd mass parent ion number. That's the M plus number. You'll have an odd number. Most of the time you have an even, okay, unless you have nitrogen and become odd. Bromine, you have like so you got bromine 79 and bromine isomer 81, and they're 50 to 50% abundant, those isotopes. So bromine, you're always going to have the M and the M plus 2. That's going to be equal height. Chlorine, you have the 2 isomers of chlorine. You have chlorine that's 37, and you have chlorine that's 35, and it's a 3 to 1 ratio. So because it's 3 to 1 ratio in nature, you're going to see that M plus 2 peak in a 3 to 1 ratio. And sulfur is the only one that has the M plus 2 peak larger than the first peak, the mass peak. So you'll see that that is larger. So let's look at this. So 158, 156, this is telling you that there's bromine. And then it tells you that the mass is 156, and you minus the mass of bromine, which is 79, and it gives you a mass of 77. Okay, so 77 is a phenyl group. So the likely proposed structure would be a benzo bromobenzene. Okay, the next one we have is, oh, I didn't tell you about iodide. Iodide has a 127 peak, and so you'll see 127. That tells you iodide. And so to figure out that compound, you'll want to do 156 minus 27, and when you do that math, you get 29, and a 29 is an ethyl. So iodoethane would be a proposed structure. Okay, so when you see this 90 and the M plus 2 is a third of the height of the 90, that should tell you that you likely have a chlorine. So then you would want to do 90 minus, what's chlorine? Chlorine is so to propose this structure here, you would do 90 minus chlorine, which is 35, and that gives you 55. Because 55 is not one of the methyl, ethyl, propyl, butyl fragments, you probably have to have an oxygen there. So you could, I mean, you could though. I would, if I was guessing, I would just do maybe something like this if you had to get a structure. I won't make you have a structure. Okay, so for this one, you want to draw the structure of 2-methylpentene, 1, 2, 3, 4, 5. And now, mass spec, this is going to bombard the sample with electrons, and then it's going to fragment. And so when you fragment, you're going to get a positive charge plus a free radical. Okay? These free radicals are not detected in the detector, but the carbocations are. So you're going to get a carbocation. And the carbocation is the one with the mass to charge ratio. So just like your more stable carbocations, that's going to be your more abundant. So explain why the M57 is less abundant than the 71 and the 43. Well, where is the M57? The M57 would be, if you broke it here, you would get that carbocation plus this radical. Okay, so this would become your radical, and this would be your carbocation. This would be a mass charge ratio of 57. But notice that that generates a this mass would be a primary carbocation right here. This would be a primary carbocation. So if you look at M43 and M71, you'll see that those give you more stable carbocations. So let's say you draw this back out. What if you fragment right here? Okay, so if you fragment right there, then you're generating 1, 2, 3, that free radical plus that carbocation. And that carbocation is mass over charge of 43. Okay, and then the other one is 71, and that would be another stable carbocation. First thing you want to do is you want to draw the structure. So there's 2,4-dimethylpentane. Now you're going to get your fragment, so you've got to look at your fragmentation pattern. If you fragment, so a lot of ways you can do this is like this. So if you fragment on this side, you're going to get a mass of 43, mass to charge ratio. So you could calculate that, and you could see that that is a 43. And then that's also going to fragment and give you this, which is a mass of 57. The 85 then would come from, if you mass that and you cleave that, so that would be an 85. And so that would look like, you can calculate the mass, meaning the carbon and the hydrogen. And of course you would get a methyl radical here, and this methyl radical is not detected, and that's your 85. Okay, so ethers are not easily differentiated by their IR spectra, but they do form predictable fragments in the mass spec. So here we have two compounds that give prominent peaks at 116, 73, 57, and 43. But one compound gives a distinctive strong peak at 87. Okay, so one gives it 87 and the other gives a strong peak at 101. Now let's draw these structures back where we can see them. You have them on your paper. And so let's look at that. So the molecular weight of each of these isomers is 116. So that's why they both give 116. The left half of the structure is the same. So if you lose the 3-carbon radical, it gives a stabilized carbocation with a mass of 73. So 1, 2, 3, 4, 1, 2, 3, 4. So if you lose this mass, 1, 2, 3, 1. So if you lose the alpha cleavage, they typically do, by the way, alpha cleavage. So if you cleave here and you cleave actually, let's erase this here. Can I erase that? Okay, good. Okay, so if you actually cleave here and then you cleave here at this alpha position, the 1, 2, 3, 4, 1, 2, 3, 4, if you do that mass fragment, you'll see CH2 plus oxygen and CH2 carbocation plus oxygen. You'd see that both of those are 73. Okay, if you lost the alpha cleavage on the other side, okay, so if you lost it here and you lost it here, you would see that this one is 87, but this one has an extra methyl group and it would be 101. Okay. Account for the peaks for the mass to charge ratio of 87, 111, 126 in this spectra below. Okay. So this has a molecular weight of 144. So 144. Yes. So C9, H20 oxygen, H20 oxygen, if you calculate it all up, it has a molecular weight of 144. So, but we don't see a 144 here. So you have to ask why. Well, in the mass spec, you're using high temperatures, ionizing conditions, so you lose a water. So when you lose a water, you dehydrate this. What will that look like? You get an alkene. See, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so you get this. And if you calculate the mass of that, so basically, what's 144 minus 18? Because that's water. You will get 126. So that accounts for the 126. It's the alkene after you dehydrate. Now, if you lose a 15, if you lose this methyl here, and you generate the carbocation, then you have what's 126 minus 15? You have 111. So there's your 111. And then the 87, so now you just have the 87 to account for, and this 87 is due to alpha cleavage of the alcohol. So if you do have the alcohol and you cleave it, okay? So if you cleave it there, then you're going, that's alpha cleavage. Remember, it likes to do alpha cleavage. And that gives you 187. I mean, just 87. Okay, so this question is talking about a foul-smelling hydrocarbon gives the mass spec and IR shown below. Okay, so this is a combination of mass spec and IR. Now, something I did not teach you in our alkene chapter, and I purposely waited to this, is to show you how to calculate elements of unsaturation. Okay, so when you're given a formula, then it's really nice to use the elements of unsaturation. Your book talks about how to do this in the alkene chapters, so let's look. So we have a mass of 110. So from our mass spec, we can figure we have a mass, a parent ion of 110. So we have a molecular weight of 110. So you have carbon and you have hydrogen. And we don't know what we have there. So this is the formula for an alkane. It's CN for however many number of carbon, and 2 times that number of carbon plus 2 is your alkane. Alkanes are considered saturated. I mean, every carbon has a hydrogen, and that's the saturated formula. So the mass of carbon is like 12. So if you take 110 divided by 12, you're going to get a number that tells you maybe 96. So that's 8 carbons. Okay. So you want about 8 carbons. Gives you about 8. And then what's H2N plus 2? That would be C8, H16, 17, 18. Okay, so that would be the saturated. If you add that up, you're going to get about 114. But you have 110. So what's 114 minus 110? It's going to give you 4. That's 4 hydrogens. So for every 2 hydrogens you take away, minus 2 hydrogens, that's 1 unit of unsaturation. That means like a carbon covalent double bond. Or it could be a ring. Okay, so a ring would be, it minuses 2 hydrogens. So that would be another unit of unsaturation. So that's what the mass spec tells us. And then you can also tell whether you have like bromine or fluorine or sulfur, those kind of things. Now, so when you look at this IR, you see this is an important peak around 2300, and that's the carbon triple bond. Okay? Well, you know you don't have a nitrogen because 110 is an even M plus number. If you had an odd number, then you could say, okay, maybe that may be nitrile. But because you don't, you have an even number, you're like, okay, this is just carbons, no nitrogens. And that right there, triple bond, is your 2 units of unsaturation. And then you have this peak here around 3300, and that is your CH from your triple bond. So that tells you right there that you have a terminal alkyne. And what did we say? We have 8 carbons. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And we have our molecular formula is C8H 14. And so we got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it is likely to be 1, 2, 3, 4, 5, 6, 7, 8. 1 octine is your structure that I would propose. Okay, this is a true story. While organizing the undergraduate stockroom, a new chemistry professor found a half-gallon jug of some cloudy liquid, marked student prep. And she looked at the mass spec and she said, oh, I know what it is, okay, without even checking the actual mass numbers. So let's look at some fragments and figure out how she figured this out so quickly. Okay, so when we look at this, we see that this 136, that's M and then the M plus 2 and is equal height. So that's going to tell you right there, you got bromine, okay? And then the other peak here is, so you take 136 and you minus bromine's molar mass, 79, and you're going to get 57. Okay, so here's 57. 57 is a butyl group. 1, 2, 3, 4. So you can figure butyl, 1, 2, 3, 4, butyl bromide. Okay, and that structure would work. You can also look at the other mass fragments of this here. That gives you a mass over charge ratio of 107, which is this one. And then if you had just the bromine and the CH3, or CH2 rather, that would be 93. Okay, a common lab experiment is the dehydration of cyclohexanol to cyclohexene. And so you need to look at the IR spectra and determine whether your product is pure cyclohexene, pure cyclohexanol, or a mixture. And so explain why mass spec might not be a good way to distinguish between cyclohexene and cyclohexanol. Well, that's because mass spec is going to dehydrate it. So you're going to lose water with your alcohol, and all you're going to see is a parent peak for the alkene. So that's why that's not a good way, okay, for mass spec. But let's look at the IR and see what we have. Well, we don't really have an IR spectra, so we're supposed to just in theory talk about how we would decide between the two. So let's just look. So you would have this OH peak here, and it would be a broad peak. It would be pretty strong, about 3,300. And then in this alkene peak, you would see a carbon-carbon double bond, and it'd be moderate around 1645. Okay, so the next one, now we're in the NMR. Okay, so that is mass spec. So we've done IR, we've done mass spec, and now we're going to talk about NMR. And in the NMR, you have some chemical shifts in a table. You also have a piece of paper that I've given you. And the table you want to look at is in your book. It's table 13.3, page 570. So 570, table 13.3. So make sure you get that. And let's just look at some of the chemical shifts we would see. So here you would have this hydrogen. It is an alkene hydrogen. That's going to show up around 5, 6 ppm. Just write the chemical shift there. This CH3 here, these hydrogens are going to show up around 0.9. Here we have an aryl CH3, so that's benzylic, and that's going to be about 2.3 chemical shift. And the aromatic hydrogens here are going to show up around 7.2 chemical shift. Here we have a CH3, the methoxy, because it's connected to the oxygen. That's going to show up between 3 and 4 chemical shift. And then your aromatic protons are going to show up around 7.2. Here we have a carbon hydrogen from the alkyne. That's going to show up around 2.5 for your chemical shift. And then this methyl is going to show up about 1.4. Actually, that's not true. I think that's going to show up around 0.9 chemical shift. Okay, here we have the aromatic hydrogens. They're going to show up at 7.2 chemical shifts. This OH is going to show up between 10 and 12 ppm, and that's because it's a carboxylic acid. These CH2s here are going to show up around 2.2, 2.1, and this is going to be around 2.3 because it's benzylic. Here we have this CH2. It's going to show up around 3 to 4, and this methyl is going to show up around 1.4 chemical shift. Determine the different kinds of protons in each compound. Okay, so you need to draw the structure. 1-chloropropane. The different kinds of protons. So for each proton that's in a different environment, it's going to have a chemical shift, a peak. Okay, so you're going to get shifts in the NMR. So when you look at your structure, you have to find out how many. You're asking yourself, how many peaks should I see? And so here you're going to have one peak there. You're going to have one peak there, and you're going to have one peak there. So you can call that A, B, and C. Okay, for 2-chloropropane, because these are symmetrical, you're going to have A, and then this is going to be B. So you're only going to have 2 peaks. You're just going to have 2 in this structure. Like I said, you'd have 3 in the first one. 2,2-dimethylbutane. So there's 2,2-dimethylbutane. Okay, these are equivalent environments here. So those are going to be A, and you're going to have one peak there. There's no hydrogen on that peak. This would be a methylene, CH2, so that would be peak B. And then this one would be peak C. So you would get 3 from that structure, 3 peaks. Okay, the next one, 2,3-butane. So there's 2, there's 3. And so, like I said, this one's 3 peaks. This one you would get 1. Those are going to be the same, A. Actually, those are all going to be the same. So you should get 1 peak for that. Just 1 peak. Okay, 1, let's draw benzene. 1 bromo. 1, 2, 3, 4 methyl. Okay, so you're looking for symmetry here. So that would be A, that would be 1 peak. These hydrogens here would be another peak, that's B, and then this methyl, which would be benzoic, would be a 3rd peak. So you would get 3 peaks for that compound. Okay, so if you do this one, 1 bromo, 2 methyl, you can put in your hydrogens in. And here you're going to have the methyl, which is the benzoic peak. And this one is different because it's connected to a methyl and a hydrogen. So that'll be B, that'll be C, D, and E. So you're going to have 1, 2, 3, 4, 5 peaks. Okay, the next compound is the NMR spectra of toluene. Methylbenzene is shown below. How many different protons are there? Well, the methyl is 1, and you see here. And then here it's a multiplet, so it's all kind of come together. But the different peaks would be, kind of just slice it in 2 here, because these hydrogens would see the same. So that would be, you can call that one A. You'd have a peak B, and then these hydrogens would be equivalent, so that's C, and then that would be D. So you're going to have 1, 2, 3, 4 different peaks, different shifts. Determine the ratios of peak areas in the following spectra. Use this information along with the chemical shifts to pair up the spectra compounds. All right, so looking at these, let's just go ahead and do their chemical shifts. And as you can see, you're going to have a peak here and a peak there. This will be about 7.2. And this is going to be about 2 to 3. And this is going to be a singlet because of the N+1 rule. The neighbors, they don't have any neighbors. These hydrogens here have a hydrogen next to it, so it's going to be a doublet. Okay, the best thing to do is just let's look at the structures here. So this structure here, you have a singlet. So you have 3 peaks, and you don't have anything in the 7 to 8, so you know you don't have any of the aromatic peaks here. So these are all aromatic, so those proton peaks would show up in the aromatic. So you're looking at these structures here. This would be a singlet with 1 proton. This would be a singlet. These are singlet, but these are going to be 6 protons. As you can see here, the height from here to here is 1 proton. So then the height, this integral from here to here is the same height, that's 1 proton. And then if you look at the height from here to here, and you add that height up, you'll see that that's 6 protons. And it's a singlet. So that would be these right here. We'll call those A. Then the OH here would be this singlet here, the OH, for the alcohol proton, which is 1. And then this alkyne would be this one here. So structure A is this compound here. Okay, so the next spectra we have is this one. As you can see, you have aromatic region, and but you only have two spectra, or 2 peaks. So you have symmetry in your molecule, and this would be the this methoxy compound, because this would be A. As you can see, if you look at the height of there, that should be 6 protons, and then these hydrogens would be about 4 protons. So that's 4 protons. They're the aromatic protons, and you're just going to get 2 peaks. So you get that peak, and we can call that B, and then you get this peak, which we can call A. There's A, and that's B. And then we have C. C, there is no aromatic, so we're looking at this compound here. So you have a bromine, and 2 methyls. So these methyls here are here, and that would be 6 protons height. And then we have the CH2 here. So this could be B, and this the integral height should be 2 protons. This is a singlet, just like these are singlets. Okay, assign protons to the peaks of NMR 4,4-dimethyl hex 2-ene-1. Explain the splitting that gives the triplets. Okay, this is the n+1 rule. So let's get this. Okay, so they're expanded here, and this is your alkene. So here's your alkene peaks. So this one would be likely HA, because it's connected to the carbonyl, and this would be HB. And then this one is a triplet. So these are doublets, because the only neighbor has 1 proton, so n+1 is a doublet. So those are both doublets. This one here is a triplet, and it's the next furthest down. So that would be likely this methylene here, which is CH2, because its neighbor has 2 protons. So there's its neighbor, it has 2 protons. So n+1, 2 + 1 is 3, which is a triplet. So that would make this a triplet. And so there's your triplet. And then the next one is likely this CH2. And you can see that's a triplet as well, because its neighbor here has 2 neighbors, so n+1 is a triplet. And then you have these methyl groups, and their neighbor right here has 0. So 0 + 1 is 1, and that makes that a singlet. And if you look at the height in here, this here is 1. This height here is only 1 proton. So this height here is 2 protons. It's double that height. And then if you look at this height here, it should be like 6 protons. Looking at the next one here, you see that this is trans. And you see that the coupling, the splitting is actually greater. So these protons, this would be A and that would be B. So there's A and there's B. And it's, look at the height, it's only one proton. Okay, the next one we have is, I would say the most downfield shift here. You see it's a singlet. It is likely this one here because of the electron, excuse me, the polar carbonyl. Okay, so that would be HC, and it's a singlet. So you can see that would be 3 protons. There's your height, and it's a singlet. The next one would likely be this methyl here. And that methyl is going to be a singlet there. So then that we'll call that, we call that one C. We call this D, and you put D there, but then we do have a triplet, let's see, so we could call this one likely the CH2 here, because it would be an electronegative environment, and that should be a triplet because it has 2 neighbors. And then we have these 2 here, which would be these methylines here, and both, one would be a triplet and one would be like a sextet. So this one would be the sextet, so this one we could call E, and then the other one would be F, and that would be that one. And then these singlets here would be 6 protons, you can see here, and they're singlets, and they shift at about 1.0 ppm. 2 spectra are shown below. Propose a structure corresponds to each. All right, so this is a little bit more challenging. The good news is we're given a formula. When we give a formula, we want to do the units of unsaturation. So units of unsaturation would be CnH2n plus 2. We're given C3H. 3 times 2 is 6, 7, 8. And when you have a chlorine, you have to minus 1. So that would be H7. And you see that C3H7. So then you go 7 minus 7 divided by 2. That's 0. So we don't have any units of unsaturation. It's always just good to do that. You see that this is a triplet, this is a sextet, and this is a triplet. So this is, at 1 is just a methyl group, and it's connected, it's just an alkane, right? And so this would give it a triplet, and it would be 3 protons. And then this would be a sextet, so what would that be? 3, 4, 5, that would give you 6 because of the n plus 1 rule here. And then we have this one, which is a triplet, and so that's 2 plus 1 is 3, and then just add your chlorine there. And so there you have propyl chloride or chloropropane. Here we have an aromatic area here. This is definitely an aromatic ring right there. We can also see we have CnH10, so units of unsaturation would be CnH2n plus 2, so Cn18, 19, 20. Then we do 20 minus 10 divided by 2. There's our 10, and that becomes 5. So we have 5 units of unsaturation. Here's 4 when you have an aromatic ring. We have 2 oxygens, so we probably have a carbonyl. I'm going to propose like an ester. And also another thing to look at is that our coupling here, we have a doublet and a doublet. So that tells you the substitution. So you have a hydrogen and a hydrogen. this aromatic ring. And this would be a doublet, and this would be a doublet. So this means this has something coming off that's different than this. And what would that be like? So here we have this group here, and it's connected to the 4. So that might be, and it looks like a singlet. So that might be an ester, CH3. And then on this side, we could have maybe a methyl group. So this is our methyl, HA. And that would be benzylic, right? Around 2.3. And then this would be a CH3, which would be a singlet. And then so you count it up, 6, 7, 8, 9 carbons. We have 3, 4, 5, 6, 7, 8, 9, 10 hydrogens and 2 oxygens. Okay, 3 proton NMR spectra are given here, together with molecular formulas. In each case, propose a structure that is consistent with the spectra. Okay, so once again, you want to do your units of unsaturation. So for this one, we would do C5H2N plus 2, and so that's C5H1012, and then we have 8 here, so 12 minus 8 divided by 2 is 4 divided by 2. We have 2 units of unsaturation. We don't have anything aromatic. So now we have to look at what we have. You can also look on page 600 of your book if you need to expand out that spectra. You'll see that this is a doublet and this is a triplet, and that is a actually this is a quadruplet, this is a singlet, and that's a triplet. So let's erase that. So this is 2 protons that are a quadruplet. This is a singlet, and that's a triplet. So, and we have 2 units of unsaturation. So a structure that would work would be something like this. CH3, carbonyl, carbonyl, CH2, CH3. So when you look at this, this would be a singlet for 3 protons. So there's your singlet for 3 protons. This would be a quadruplet for 2 protons. This is a quadruplet for 2 protons. This is a triplet for 3 protons. And we have 5, 1, 2, 3, 4, 5 carbons, 3, 4, 5, 6, 7, 8 hydrogens, and 2 oxygens. And these are 2 units of unsaturation. Okay, so let's do the units of unsaturation again. C4H8, so that is C4H2N plus 2, C4H8, 9, 10, so H10, 10 minus 8 divided by 2 is 2 divided by 2 is 1. So we have 1 unit of unsaturation. This offset means it's around 12.4 ppm. It's a broad OH. So that's telling you a carboxylic acid. Okay, so that's that proton right there. And that gives us our 1 unit of unsaturation. And we've used up a carbon and a hydrogen and 2 oxygens. Now we have to figure out what's on this side. And so if you do something like this, you'll see that this is a CH3 and a CH3. So this is a doublet. You might need to look at that in your book to see that it's a doublet for 6 protons. This would be a doublet because this is a hydrogen here. So this would be A. And then here we have 1 proton, and it is a 3, 6, it's a 7-tet, quintet. So and it's 1 proton. So this is your structure, C4, 1, 2, 3, 4, 2 oxygens, 3, 6, 7, 8 hydrogens. Okay, so here we're going to do our units of unsaturation again. C9H 2N plus 2, C9, 9 times 2 is 18, plus 2 is 20, 20 minus 10, we got 10 right here, divided by 2 is 5, or 10 divided by 2 is 5. So we have 5, and you see this is an aromatic ring. So go ahead and draw your aromatic ring, that's 4 units. This at 9.8 lets you know that you have an aldehyde proton, okay? So you have an aldehyde. So go ahead and figure out where that is. This is going to be 5 protons. It's kind of all together, so there's no like doublet and 2 doublets, so it's going to be like that. These here are like a CH2 because the benzylic would be around that area, and they're 1, 2, 3. They're both triplets. So that's a CH2 bonded to a CH2, so that would be a triplet, and that would be a triplet, and they're both 2 protons, and then you'd have your aldehyde. So if you counted up how many carbons you have, 6, 7, 8, 9, you have 1 oxygen, and you have 5, 6, 7, 8, 9, 10 hydrogens. So you have this aromatic aldehyde. This problem is talking about carbon NMR, and we are to look at 4-hydroxybutanoic acid. But this was not the compound that was obtained. See, a different compound was obtained. So you have 1, 2, 3, 4 peaks. So that means you have 4 different carbon compounds. And you see you have, okay, so instead of this compound, so let's just look what was expected. 1, 2, 3, 4. This is the 4-hydroxybutanoic acid. Got another compound, and this compound here would have 1, 2, 3, 4 carbon peaks, but this is different. And this peak here, we'll call A, is different. Is definitely the carbonyl peak. Okay, it's around 180 ppm. So the proposed structure would be, I'm looking to see, oh yeah, this is key here. You see that we have C4H6O3. So let's do our units of unsaturation. So C4H2N plus 2. So this is C4, 8, 9, 10, H10. You have 6 there, so 10 minus 6 divided by 2 is 4 divided by 2. So there's 2 units of unsaturation. So what I'm going to propose is a ring closure, and you lose water. Okay, so if you lose this OH and that H, because you're heating this, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5-membered ring. This is A, carbon number A. Let's see, 1, 2, 3, 4. That's 4 carbons. 1, 2, 3, 4, 5, 6 hydrogens and 2 oxygens. All right, so then this would be carbon number B right there, because it's bonded to an oxygen. And then you'd have C, which is alpha to the carbonyl group, and then D. This problem is trying to convert cyclohexanol to cyclohexylbromide, but that was not the product. We still have C6H10. So let's just do our units of unsaturation. C6H2N plus 2 is C6, 12, 13, 14, 12, 13, 14. 14 minus 10 divided by 2, the 10 there, is 2. And this is only 3 compounds. So what if we got elimination? And you got that. That would be C6, and that would be 1, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you would have 3 different peaks because there's symmetry here. So these peaks would be H or carbon A, and then this methylene would be B, and then this one would be C. And you would only get 3 peaks because these would be equivalent. An unknown compound has a molecular formula of C9H11 bromine. And it's just telling you what the NMR is. So let's do our units of unsaturation. C9H11 bromine. So CnH2n plus 2. And then with bromine, you have to subtract 1 for group 6. Group 7s. Group 6, you don't do anything. So oxygen, you don't do anything. If you have a group 5 element, then you have to add 1. So this is C9H 18, 19, 20. 20 minus 1 is 19. And then it's 19 minus 11 divided by 2. That's 8 divided by 2. So that gives you 4 units of unsaturation. You also have, this is proton NMR. You have this integration at 7.1. So that's indicative of an aromatic ring. And then the other thing you have is the height. This is the integral height. And you see you got 44 millimeters, 130, 67. And this is going to give you how many protons you have. So we divide everything by the lowest number to get whole number ratios. This would be 1 proton. Then 130 divided by 44 is going to give you 3 protons. And then 67 divided by 44 is going to give you 1.5. So because that's not a full integral, and you can't have 1.5 protons, you're going to have to divide all or times all these by 2 to get our true count. Okay, and that's 3, that's 6, and that's 2. So add these up. 2 plus 6 plus 3 is 9, 10, 11, and there you go, there's 11. So, but let's look at this a little closer. So in the aromatic region, we have 2 protons. So that means there's only 2 protons, and they're equivalent to. And then here you have so you only have 2 protons coming off this aromatic ring. So the question is, where are they located? You also have a singlet at 2.3. So that means you got some benzyl protons. And at 130, you have 6 of these. So there's benzyl protons at 2.3, and that would be 6 of them. 3 and 3 would be 6. And then you also have 2.2. So just go ahead and put another one on there. And that would be different because it's slightly shift. And then that would give you this proton here and this proton here. And that should work out. 6, 7, 8, 9, 3, 6, 9, 10, 11, and 1 bromine. Okay, predict the multiplicity. It means the number of peaks as a result of the splitting and the chemical shifts. Okay, so this carbon, this 3 protons are next door to this one, and that one has 2. So we're going to do the n plus 1 rule. N is the neighbor, so 2 plus 1 is 3, so that's a triplet. And the chemical shift here would be about a 0.9 chemical shift because it's just next, it's a methyl next to a alkyl group. This one here, then this neighbor doesn't, so it has 2 neighbors, neighboring carbon. One doesn't have a hydrogen, the other one has 3. So that would be a quartet, which is 4. So n plus 1 is 4, and that would be maybe go with a 2.2 chemical shift. The reason why is it's next to a carbon with chlorines. And then this one doesn't have a neighbor. Okay, there's no neighbor there. So it would be a singlet. And you could say about 1.78 chemical shift. Okay, going over here. This one here would be a doublet, but it would, since it's an OH, it's probably a broad singlet, and that's about 2.5. It can be variable because it's on oxygen. If it's on oxygen or nitrogen, it's hard to predict where they're going to show up. And they're going to be broad singlets. This one here, the neighbor has 1, so that's going to definitely be a doublet. And since it's next to connected to an alkyl group, you can just go with 0.9 chemical shift. And then this highlighted hydrogen is bonded to 3 neighbors, so that would be a quartet. And since that's bonded right to an oxygen, a carbon with an oxygen bond, you're going to look at about 3 to 4 chemical shifts, 3 to 4 ppm. All right, so going over to C, this one has 3, 6, 9 neighbors. That's going to be like a major multiplet. You're going to have 10 peaks, and that's going to be about 0.9 chemical shifts because they're actually about a 1.4 because it's a methyne rather than a methyl. And then the methyls are going to be 0.9 chemical shifts, and this only has 1 neighbor, so it's going to be a doublet. Okay, coming down to here, we have this methyl coming off the aromatic ring, so that carbon there doesn't have any hydrogen, so that's going to be a singlet, and it's going to be about 2.3 chemical shift because it's benzylic. And this hydrogen here is bonded, its neighbor has 1, so that's going to be a doublet, and it's going to be about 7.1 ppm or 7.2. Okay, going to this one. This one would be a singlet, and it would be about 0.9 chemical shift. This is got a neighbor of 3, so that's a quartet, 4, and that's bonded to an oxygen, so I'm going to go with 3 to 4 chemical shift. This is next to this, which is a it's got 2, so that would be a triplet, and that would be about a 0.9 ppm chemical shift. And coming over here, this would be a doublet, and so just probably 0.9 ppm. And this one here, the carbon bonded to an oxygen, the hydrogen, that has 3, 4, 5, 6 neighbors, so that's a sextet. And it would probably be a 3 to 4 ppm because that carbon is bonded to the oxygen, which is very electronegative in deshielding. Predict the approximate chemical shifts in the protons of the following compounds. Okay, benzene, they're all going to be around 7.2 ppm. Cyclohexane, so let me draw benzene so you know. That's benzene. Cyclohexane is going to be, they're all going to be about 1.3 ppm. Okay, here we have this, we just want the chemical shifts. This carbon is bonded to an oxygen, so that's about 3 to 4 chemical shift. So this one's about 3 to 4. And this one would be about 3 to 4 because it's bonded to a chlorine. And then this one would be less, it'd be about a 1.3 ppm because it's bonded to carbon on both sides. Okay, coming here, this one would be about a 2.1 chemical shift. This one would be about a 2.2, and this one would be about a 1.0 chemical shift. This one here, about a 2.1. This is a 2.1. This is a 0.9. Coming over here, the OH is anywhere from 2 to 5 chemical shift. Since this carbon is bonded to that oxygen, it's going to be a 3 to 4. This carbon is bonded to this oxygen, that's going to be a 3 to 4, somewhere between 3 and 4. This hydrogen is going to show up somewhere between 3 and 4. And then these methyls are going to show up about 0.9 chemical shift. Okay, so the hydrogens here, they're not drawn in G, all going to show up about 7.2 ppm. This aldehyde proton, 9.8 ppm. That's important. You can always tell if you have an aldehyde. This one, the aldehyde proton, 9.8. This alkene or vinyl proton connected to the carbon, it's a carbon-carbon bond, it's an sp2. It's going to show up between 5 and 6. Same thing here, between 5 and 6. And this methyl here is allylic because it's next to an sp2 carbon, and that's going to be about 1.7. Carboxylic acid is going to show up between 10 to 12 ppm. This is an alpha carbon, so it's next to a carbonyl, that's 2.1. Same thing with that one, is at 2.1. This CH is connected to oxygen, so that's going to be about 3 to 4. And then this methyl is connected to just a carbon, an alkyl group, so that's a 0.9. Okay, these hydrogens here are connected to sp2 carbon. They're vinyl, so they're going to show up between 5 to 6 ppm. And then these are methylenes, and they're allylic, okay, because they're next to the carbon that's an sp2 carbon. That's going to be about 1.7. And then these CH2s are all going to be about 1.3. Okay, indane, all these hydrogens coming off the aromatic ring, they're going to be about 7.2. These CH2s that are connected to the aromatic ring are called benzylic. And so benzylic are going to show up about 2.3. And then this CH2 is going to show up about 1.3. Indene, so once again you have the aromatic protons that are going to show up at about 7.2 ppm. You have this benzylic CH2s, they're going to show up about 2.3 chemical shift. And then you have these hydrogens here. This hydrogen is going to be more downfield. And they're going to show up about 5 to 6 ppm. Okay, the following proton NMR spectra is a compound with a molecular formula of C3H8 oxygen. Propose a structure and assign those peaks. Okay, well, once again, let's do units of unsaturation. C3H8, C3H2N plus 2, So it's 6, 7, 8, C3H8. H minus 8 divided by 2 is 0. So there's no units of unsaturation. So there's no carbon-carbon double bond. There's no ring. You see that we have okay, so what's our height here? You might have to look at your book if that's hard to see, but let's see. That's a height here. That height of that integral is going to tell you how many protons. We gotta count for 8 protons. This is pointing there, so it's a doublet. And this is pointing here, and it's 1, 2, 3, 4, 5, 6, 7 peaks. Okay, so those are your n plus 1. That's your splitting. So that tells you your neighbors, n plus 1. And then this is just a broad peak. We have O there, so that's likely an alcohol peak. And remember, that can be a broad singlet between 2 and 5. It can be variable, so it's between 2 and 5. You have an oxygen to account for, and you cannot have an oxygen-carbon double bond because you have 0 units of unsaturation. So, and this is going to be 1 proton. So you see the height there. So this would be 1 proton. And then, so that's 2. This would have to be 6 protons. So if you do the height, you can get like a little paper edge and a ruler and figure out the height. So that would account for your protons. Okay, so if this is a doublet, then that means that the neighbor has to have 1 proton. So you could see that these are around 1 ppm. Okay, so that's a chemical shift of an alkyl group connected to a carbon. And then the neighbor has 1 proton here. So that would make this a doublet and this a doublet, and they would be equivalent. And there's 6 protons. So that would be this piece here. And then this could be connected to an OH, right? So does that carbon have 4 things? 1, 2, 3, 4. So there's your OH. And then, is that 7 peaks? How many neighbors does this carbon have? 3 plus 3. So n plus 1. 6 plus 1 is 7. And that CH would be around 4 because that carbon is connected to the oxygen. So that is your structure. Okay, a compound with the structure C10H12O2 was isolated from a mixture containing, let's see, 2-phenylethanol. So this plus acetic acid. Now what you might not know is this is called esterification, and this will make an ester. This alcohol will combine with this acetyl group to make an ester. So this reaction is this. And so let's count the carbons. 1, 2, 3, 4, plus 6 is 10. H12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 2 oxygen. Okay, so then let's look. Here's 5 protons. You see the 5? And they're at 7.2, which would be these 5. Okay, so that's your aromatic. Then you have 2 protons here at 4. So, 2. Oh, so I drew this wrong. It's this. Okay. This oxygen's here, and then you make your ester. So once again, here's your 5 protons at 7.2, And then these two protons here, these two protons are these right here. Okay, because they have to be connected to a carbon that's connected to an oxygen to show up at 4. And then these two protons are around 3, and so those are benzylic right here. Between 2 and 3 are benzylic. And then you have 3 protons here that are 2, and that would be an alpha to the carbonyl group. So there you go. Okay, I've decided to omit this, so I don't want you to have to do it, so you can just write omit. If you want to do it, then you can come check your answers with me if you want. You can omit that, and you can omit this one, okay? So you can omit that one. So you can check your answers with me if you still want to do it, but you can omit it for my purposes. And for each pair of compounds, decide which instrumental technique, IR, mass spec, proton NMR, carbon NMR, you would distinguish these compounds. Okay, so this one, they're going to give you a similar mass spec, but you could use carbon NMR or proton NMR. So you'd be able to distinguish that. This one here, they're both esters, so, and both ethers. These are both ethers. So since they have the same functional groups, you can't really use IR. Here, these are both esters. Well, actually, this is an ester, and this is a ketone and an ether. But the IR would be hard to tell because you got a carbonyl and similar. But you could do proton and carbon NMR. Your mass specs are going to look similar. So this one here, mass spec would be excellent for. Okay, mass spec's going to, molecular weights can be very different with the chlorine versus the fluorine. This one here, once again, we have 2 esters, so you're not going to really use IR. You could use proton NMR or carbon NMR. And on your assignments, you have the worked example problem 2, so number 33 and 34 that are attached. We will go over these in class, so just go ahead and try to problem solve those structures.